Okay. Let us keep going with rotation. So rotational motion, and we're starting to build towards rotational dynamics. Again, we are essentially flying through the first 20-ish lectures of this course again, but doing it all with rotation instead of with linear translational motion. Again, the good news is that most of what we've seen before has an analogous, very similar looking version in rotation, though rotation is a little bit more abstract to imagine and visualize because it involves things like the right-hand rule. So to recap, right, that we have something that's undergoing rotational motion. We specify rotational motion by, we can quantify how fast it is, in this case the ball on a string, is going through 2 pi radians. What is the period of this object? It goes in a full circle in some amount of time. That defines what we call an angular velocity. An angular velocity of how many radians per second this ball is sweeping out. And in doing so, we can specify a vector that corresponds to the angular velocity, which is a vector that points along the axis of rotation. The axis of rotation was a point or a line that specifies where the object is rotating around. Where's my hula hoop? For example, like this thing here, like I could rotate this thing in multiple ways by having different axes of rotation. If my axis of rotation was right through the center of the hula hoop, that would be an example of, say, this sort of rotation. The entire hula hoop is rotating about this axis of rotation here. I could also rotate this object about this axis of rotation. Use my other hand. In which case, this would be the rotation of the hula hoop. The entire thing is rotating about this axis of rotation, which looks quite different than, say, just like this. Or similarly, I could have an axis of rotation that goes straight vertically up and down. So that would be rotation that looks like this. That is a different kind of rotation. That would be specified by a different axis of rotation and might have a different angular velocity. So you specify, in specifying the vector for the angular velocity, what you're specifying the, before we said that a vector is a length and a direction. In this case, this vector is still a length and a direction, but the interpretation of the direction is that omega, the angular velocity, points either parallel or anti-parallel to the axis of rotation, and that specifies what direction the object is rotating based on the right-hand rule. Again, the right-hand rule being that you use your right-hand thumb, put it either parallel or anti-parallel to the axis of rotation, and then your fingers curl in the direction of motion that the object is moving. So in this case, where it's rotating like this, to me it's rotating clockwise. It might be reversed on the video. But either way, we can both agree on the axis of rotation, because since I see the ball rotating a certain way, I can make my fingers curl in the same direction that the ball was spinning in, and then my thumb points in the direction of the, along the axis of rotation, in the direction I would draw omega. So I guess for you, it would appear like the axis of rotation is going, or omega rather, is going out of the screen. We also saw that all the angular variables obeyed the same relationships between angular displacement, angular velocity, angular acceleration, again related by the derivative, and then similarly if you wanted to go the other way, they would be related by the integral, just like it was in linear motion. Here we're not measuring in meters, but we're measuring in radians, and that is key. It must be radians. If you do things in degrees, you will get the wrong answer. And so things like what we saw with kinematics follows directly. When the angular acceleration is pointing along the same direction as the angular velocity, that would be an example of the rotation speeding up compared to what it was before. If the angular velocity is in one direction and the angular acceleration is in the other, that would be an example of the object slowing down in its rate of rotation. And then if they are pointing in different directions, we will see a little bit, not when we get to dynamics, that this will both change the direction of rotation and the magnitude. So it could start out doing something like this, but it could rotate to end up being something like this, for example. It had undergone angular acceleration as a result. Just like what we saw with linear motion. And similarly, if omega is a constant, the angular kinematic equations apply. They have the same form as the linear ones, but we use angular variables. How about an example? What is omega of a clock minute hand? You find an analog clock. There's a minute hand that rotates around. What is the angular velocity of the minute hand? So angular velocity is radians per second, or angle over time, really, is one example. The MKS version would be radians per second. In which case, I could say for the minute hand, it completes one full loop. So it completes one loop, or 2 pi radians. Every what? How long does it take the minute hand to go around once? Every 60 minutes. So and then I might say the angular velocity of the minute hand is 2 pi divided by 60 minutes. Would be the angular velocity of the minute hand. And that is exact because it turns out that the minute hand is moving at a constant rate. Time moves at steady increments. So the minute hand, the second hand, the hour hand are all moving at some constant rate. So they're moving at different rates. Unless they were moving at the same. For example, what is the angular velocity of the second hand? In that case, it goes through a full circle, not every 60 minutes, but every 60 seconds. So its angular velocity is much larger than the minute hand. 60 times larger. And then I'll let you think of what it would be for the hour hand. Suppose a pitcher in a baseball game throws a ball with a velocity of 85 miles per hour. They give the ball a spin. This is based off some problem in the book, so I apologize, I forget which one. They give the ball a spin of 1,800 revolutions per minute. Where one revolution is, of course, 2 pi radians. One full, this is not baseball, but one full rotation. The distance to the batter is 60 feet. I could ask, how many rotations does the ball complete? In the air. Pitcher throws a ball. It's moving at 85 miles per hour. It has to travel 60 feet. The pitcher gives a spin to the ball, so the ball is spinning while it's flying towards the batter at a rate of 1,800 revolutions per minute. How many revolutions does it complete in that time? So in this case, we're combining linear and angular motions. There is a ball that travels 60 feet to some bat with the idea that the velocity is approximately constant at 85 miles per hour. And if we're looking at the horizontal motion, there's no worry of acceleration or anything like that. Though I think the problem said to ignore it. So in that case, we know then that the distance traveled, or the change, the displacement, is some initial velocity times time plus 1/2 whatever the acceleration in the horizontal direction is, t squared. This is the horizontal direction, so then we just get that d, if I call this 60 feet d, and this 85 miles per hour v naught is just v naught, and this is some delta t. Delta t, distance over velocity. You have to be careful with your units, because notice there's miles and there's feet, there's hours and there's seconds. Well, there's no seconds. But I'll tell you, the answer is 1/2 a second. With that information in mind, we can then ask ourselves, how many revolutions does the ball complete? If it completes 1,800 revolutions per minute, that's saying that the angular velocity is 1,800 rev per minute. And so if there's no angular acceleration, then I would expect delta theta to equal omega naught times delta t. You know, the same sort of kinematics relationship. To which case then I would do 1,800 rev per minute, multiplied by 1/2 of a second. But 1/2 of a second, I could also convert that into minutes as well. So the minutes cancel. And assuming I did not make a mistake, though the zero cancel, get 15 revolutions. Not too bad. I'll do one more. You have a disk rotating with 120 radians per second. Slows to rest with constant acceleration in 10 seconds. What is alpha? Or I could have asked, what is the average value for alpha? In this case, we have the second kinematics equation where omega final equals omega initial plus alpha t. You know, we had a similar one for velocity, now we have one for angular velocity. It slows to rest, so the final is 0, this is 120, this is unknown, and this is 10. So then alpha in that case is negative 12 radians per second squared. And in this case, that would be like a spinning disc, right? That slows down and down and down like an old school record player, where the disc slows down and eventually comes to rest. If it does it at a constant rate, you can use the kinematic expressions. Okay. Let's think of how we relate the linear and angular variables. You can take the example of the spinning ball. The spinning ball, I'm spinning it in a circle. If it's spinning at a constant rate, i.e. not hitting my leg, if it's spinning at a constant rate, then we already have studied this problem a little bit, where we can specify that if it's spinning at a constant rate, this is uniform circular motion, and I could write down some expressions to quantify what that means. I'm going to make the circle smaller. Uniform circular motion also means that the object is spinning out a constant angle at a constant amount of, or in the same amount of time. Its angular velocity is constant in this case, 12 radians per second or something like that. Something that depends on how fast it's sweeping through the circle. Though presumably how fast, if it's rotating really fast versus if it's barely rotating at all, if I look at the velocity of the ball at the end, the velocity of the ball, that is how much it's moving, like when it's at the top, it's moving in this direction, and when it's on the side, it's moving in this direction. The magnitude of that velocity clearly depends on whether or not the object is spinning fast or slow. Presumably there is a relationship relating the angular quantities, angular velocity, angular acceleration, to the linear quantities, like just velocity, just acceleration. So let me draw a picture to represent that. You have some arc of a circle. This is just part of a circle. And it's rotating about some axis of rotation. And the object has some velocity that is changing direction. May or may not also be changing magnitude. It could be speeding up or slowing down as well. There's some theta here. And the distance between the axis of rotation and the object itself we will call r, to quantify it as kind of the radius of the circle that the object is tracing out. And in this case, it looks like it's going counterclockwise. So if I look at it on the screen and curl my fingers in the counterclockwise direction, then omega would point out of the screen. Remember, that is a circle with a dot, means out of the screen, or out of the page. I think the idea is that you're supposed to think of it as an arrow tip. And if you're looking kind of face down on the arrow, you see the very tip of the arrow with a circle around it. I think that's the idea. I don't know. I could have just made that up. Where's my copy? Y than the other one's an X? I don't know. All right, so we've specified kind of, there's some relationship between all of these objects, or all these quantities rather. Some of them we have seen before, actually. If I draw another picture to correspond to the same thing, just because the one on the top is getting a little busy. We talked about how for an object to move in a circle, there must be a centripetal acceleration that exists, something that causes the direction of the ball, in this case, to always be changing. So we talked about how there must be a center-seeking centripetal acceleration as well. And we had written down what that centripetal acceleration is as v squared divided by r. though that really is only relating linear variables to linear variables. Now we want to work in the other variables. So this is the center seeking component. And then let's just put it all out there first, and then I'll just derive all the answers at once. It could also be the case, and we talked about this as well, this was a quiz question even, of you have something spinning in a circle. There must therefore be centripetal acceleration that brings the thing towards the center of the circle. But then what if the spinning is speeding up or slowing down? We know the velocity can only speed up or slow down if there is an acceleration in the direction of motion or anti-parallel to the direction of motion. So it could be, if the object is speeding up or slowing down, that there could also be, say, a tangential acceleration. Right, this is the speeding up down part, and this is the direction changing part. And we've seen this so many times now already, but now I'm just recasting it again in terms of circular motion. So how could I specify that in terms of all of our angular variables? This is the direction changing. No, sorry, no, that's wrong. This is the speed changing, or the magnitude. Alrighty, how can we write all these down? It all starts with the expression we had for the arc length of this arc. I have to yet again draw another version of this. You have some axis of rotation. It's sweeping out a circle that has some radius r. And when it goes some angle theta, it covers some distance of arc length s. Some fraction of the full circle. And then if you go a full 2 pi radians, of course that just becomes the circumference of the circle, which you see you get from this expression if you plug in 2 pi for theta, since we must always work with radian measurements. So you can think of this as the arc displacement. Or how the position is changing along this rotational motion. So then you might say that then the velocity of the object would just be the derivative of this arc displacement. How quickly is it moving across these arcs as it tries to trace out a full circle? Which then is just the derivative of the right-hand side. But the radius is not changing. The circle, in this case, is not getting any bigger or smaller. So that can pop out of the derivative, and this just becomes r times omega. Or, as it's usually written, v is omega r. You can relate the tangential velocity. How quickly, if I were to have a little speedometer at every point, what would that speedometer be reading? It depends on the angular velocity and how far away you are from the axis of rotation. So again, angular velocity. This is radius, or you can think of it as distance from axis of rotation. And what can we think about what that means? Suppose I have a rod and I put a bead here and a bead here, halfway out and all the way out. And I put my axis of rotation here at the edge, so it's rotating in this fashion. Or I'll just do it vertically so you can see the entire thing. So it's sweeping out a full circle And suppose that, and I think we looked at this last time, if the entire rod is moving at a constant angular velocity, that means the entire rod, every piece of the rod, no matter where you are on the rod, completes 2 pi radians in the same amount of time. Angular velocity relates to how the entire object is rotating, which means the bead in, and suppose that period is a second. So that means in 1 second, this bead in the center sweeps out a full circle. That also means in the same second, this outer bead traces out a full circle. But if you look at the distance that they had to cover, if this is the rod, and then it's sweeping out a full circle, so I'll draw it at a couple other points. And then suppose there's a green rod in the center, and a red bead at the tip. And what this is saying is in 1 second, the red bead sweeps out this entire thing, this entire circle, while the green bead then sweeps out a full but smaller circle. The green bead covers less distance. In the same amount of time. Where the red bead has a much larger circle it has to get through. It has to cover, right, its Fitbit has to log more steps in order to get through that full larger circle in the same amount of time. Therefore, that red bead has to be moving faster in order to sweep out that full larger circumference. So that kind of helps my intuition with why velocity must scale as the radius. Oops. Then we could ask, how is this velocity changing? The tangential acceleration is then just, again, the derivative of the velocity, which in this case is just omega multiplied by r. Again, r is a constant. The derivative of omega is alpha, so then this becomes just alpha times r. Whether the object is speeding up or slowing down depends on if there is a tangential or parallel antiparallel component. That is just given by alpha times the radius, or the distance from the axis of rotation in this case. So then our relationships are that there's some arc, which is r times theta. The velocity is related to r times omega. The tangential component is r times alpha. And then the centripetal component relates to v squared over r. But if I wanted to use the angular variables, we just derived that v is the same thing as r omega over r. So this then appears to be, see, it's r squared omega squared over r. One of the r's cancels. This is r omega squared. Of how you can relate the linear variables to the angular variables. Some other things you might say, right? What is the period of rotation? Remember, that was how long it takes to complete one full circle. Previously, we defined it as, well, it has to travel the full circumference of the circle, and it's doing that at some velocity. How quickly does it cover a certain distance depends on, distance divided by the velocity it's covering that distance. If we wanted to, we could replace v with r omega. And notice that in this case, the period is just 2 pi divided by omega to get the period of rotation. We will see this again when we do oscillations. 2 pi over omega is a good quantity to have in mind, because if you know the angular speed, angular velocity, And you're dealing with circular motion, oscillating motions, motions that repeat itself, like, shaking a spring up and down, or slinking up and down. I guess you could do a spring too. 2 pi over omega gives you the expression of the period. And sometimes you see the frequency, which was defined as just 1 over the period, the frequency of rotation, which in this case is just omega divided by 2 pi. Easy enough. Remember, the units of frequency was hertz, and then this is has frequency. Period has units of seconds, or time rather. And if it's 1 over seconds, that is a special unit which we call the hertz. Right. So in the case of the beads. Right, this is the green bead, this is the red bead, and they are rotating, maybe they're on a record player, right, so they're rotating at some rate. Perhaps I say that it's rotating at 1 rev per 5 seconds. What is the velocity of each bead? How fast is the green bead moving? How fast is the red bead moving? This can be important if, for example, there's, perhaps this was a speck of dust on the record player. One of those would be more prone to be flying off the disc because friction would be unable to hold it onto the disc, for example. Let's see, so we're told that the angular velocity is 1 rev per 5 seconds. Or 2 pi radians per 5 seconds. Maybe just to give us some MKS units, right? 2 pi divided by 5, which is about 1.26 radians per second. That then suggests that the velocity of the red bead is omega times, I guess I did not give the radius of this. All right, let's suppose this is, just keep the numbers simple, 10 centimeters, 0.1 meters. So then in this case, you would plug in 0.05 meters. So 1.26 times 1.05, looks like that is 0.063 meters per second. Where the velocity of the green bead is the same omega, but now multiplied by the full radius, which is just twice as much. So it would have a velocity of 0.126 meters per second. The green bead has a larger overall velocity. If the record player is rotating at a constant rate, that means omega is 0. That then implies the tangential acceleration is 0 for both. The bead is not slowing up, speeding up, or slowing down as it goes in the circle, but it nonetheless is experiencing an acceleration. There's a centripetal acceleration, v squared over r. You could use that. We just calculated the v's, and then one has a radius of 0.05 meters, and one has a radius of 0.01 meters. So 0.1 meters. Or you could use r omega squared as a identical relationship for those. In this case, I could take 1.26, I could square it first, and then multiply it by 0.05, in which case, for the centripetal acceleration for the red bead, I get 0.079 meters per second squared. For the green bead, the omega is the same, but the radius is twice as large. So then this is 1.58 meters per second squared. To rounding error, I guess. Did I do the colors wrong? I did the colors wrong. Crap, I've been doing all the colors the opposite way. I'm sorry. We can keep all the numbers the same, but I've been doing it as if the green dot was here and the red dot was here. Apologies. Okay. Is that the end of the page? That's the end of the page. We're heading towards dynamics. Kinematics was all well and good, but that just allows us to be able to explain motion. It does not tell us why the motion occurs. To explain how motion occurred, we had Newton's laws of motion, which of course still apply even if the motion is rotational. But is there now an analogous way we can write down Newton's laws in terms of rotational variables? We will do that next lecture. To motivate it with this lecture, we have to talk about mass. Mass played the role of being, or inertia, played the role of being the tendency for an object to want to stay in motion if it's already in motion, or the object's tendency to stay at rest if it was already at rest. It was the relationship between force and acceleration. The relationship between the two was the mass of the object. A more massive object takes more force to accelerate for a given acceleration. So the question here is there an analogous idea for rotation? We can think of this kind of, maybe before I even get there, we can just kind of prime the pump, that some rotations are easier to do than others. For example, if I take this rod, and you can do this with your pencil or your pen, I could take this rod, I could rotate it in multiple ways. I could have the axis of rotation kind of go here in the center, in which case it's this sort of rotation. I could have the axis of rotation along one end, in which case it's this sort of rotation, which is a little clunkier for me to do. It takes a little bit more effort in an imprecise, non-physics sense of the word. It takes a little bit more effort on my end to get this sort of motion. I could also have the axis of rotation go down the tube, in which case this is what the rotation would look like, just kind of rotating it in place, which is very easy for me to do. I could do this all day, where this would be, eventually would get kind of exhausting. Right, similarly with the hula hoop, right, it's easy when the axis of rotation is here. It's easier for me to do this and kind of just rotate it, in place, as opposed to if the axis of rotation is right here, in which case, this sort of motion takes a little bit more effort to get the hula hoop rotating like this compared to when it was just doing this. Or similarly, when it was just doing this. In both this case that I'm doing right now, and in this case, where the axis of rotation is here and I'm just spinning, in that case, the mass that actually makes up this hula hoop is all kind of symmetrically the same distance away from the axis of rotation. In this case, and in this case, there's some symmetry about how the mass is distributed about the axis of rotation. Versus here, all of the mass is either down here at one point, over here, up here. There is some mass that is always very far away from the axis of rotation. And that's a similar idea with the rod. You know, this has a lot of the mass, you know, like this part of the mass over here, is very far away from the axis of rotation. Compared to when I do this, all the mass is essentially just right along the axis of rotation. It's very close to the axis of rotation. The radius, quote unquote, the distance from the axis of rotation, for all the mass is very small in this case compared to in this case. There's some parts where it's really far away. And that's important, right? Because when we did circular motion, you know, if something's in uniform circular motion but has a larger, it can't be infinitely large, has a very large radius, if it's moving at the same angular rate, we just wrote down that the velocity of the ball must be very large when it has a large radius of rotation compared to when it's very small and is rotating at the same angular rate. Sweeps up the same number of degrees every second for the small circle and for the big circle. The ball must be moving faster the farther away it is. So if I take the example of like a pendulum, or in the case of what you did for lab, like a canonical pendulum, you know, I might want to ask, what sort of kinetic energy is associated with this canonical pendulum? There's clearly mass that's moving, so there clearly is kinetic energy in the problem. But could I quantify that in some way? That might yield a clue as to how I quantify how this kinetic energy is different than, say, if I do have the same circle or the same rotation rate, but a larger circle. Let's start with the simplest case. Let's take the ball and the string like I've been doing, where we can ignore the mass of the string, and I just have a ball that's on the end of a string. The string's radius r, and the object is rotating around in a circle. It's a spinning ball on string. What is the kinetic energy of the spinning ball on the string? To remind us, because again, knowing that we're analogies will bound, what I'm asking is, with linear kinetic energy, we wrote something like 1/2 mv squared. If we want to go to some angular analogy, is there something that I could say 1/2 something omega squared? It can't just be the mass. The units would not make sense. That would not be kinetic energy. Kinetic energy still better have a unit of joules. But if I take angular velocity squared times mass, that does not have units of joules. So is there something else that can play the role of mass and could allow me to write kinetic energy in a very similar way like we did before? In this case, it's pretty easy to write down for just a single particle. So the kinetic energy is defined as 1/2 mv squared. But the velocity of the ball in this case is from circular motion. It's going around in a circle with radius r at some angular velocity omega. We just wrote down that the relationship is the velocity is omega times the radius. So then if I square this out, notice that it gets into a form that looks like 1/2 times something times omega squared, which kind of looks like 1/2 mv squared. But now instead of mass, we've replaced it with mass times the square of the distance. Mass times distance from rotation axis squared. We call this the rotational inertia. Also sometimes called a moment of inertia. I think rotational inertia is more telling, and it's also what your book uses. Though I admittedly was brought up calling it moment of inertia, so if I slip, I apologize. But they mean the same thing. So this is a quantity that is saying something about how hard or easy it is to get something rotating. Before, it was just the mass, the linear inertia in a sense of how hard or easy it was to get something to move. This is specifying that it's not just the mass that matters, but it's how far away the object is from the rotational axis. It is harder to get something moving when it is far away from the rotation axis compared to if it's, very close to the rotation axis and everything is very centrally concentrated. The rotational inertia, the mass of rotation, depends not only on the actual physical mass, but also on the distance the object is from the rotation axis. So that also means, I think this is even worth writing down, that means the same object can have different rotational inertias for different axes of rotation. And again, going back to the rod, the rotational inertia I would calculate if I were to be rotating it like this is different than the rotational inertia I would get if I were doing it like this. It takes more on my end to rotate the hula hoop in this fashion compared to what it takes for me to rotate the hula hoop in this fashion. In those cases, there would be different moments of inertia which depend on how and where you specify your rotational axis. What if we have a baton? So I guess this is not quite a baton, but it's long enough for me to use. But I have a baton, and there are two masses at either end with a very thin rod in between. What is the rotational inertia of the baton? Now, given what I just said, that's an ill-posed problem. If I just said, what's the rotational inertia of the baton? You would respond, you have not given me enough information to answer the question. Because I also have to specify how I'm rotating the baton. Am I rotating it like I've been doing, like this? Or am I rotating it like this? Or am I rotating it like this, on one end? You get different answers for each. So let's assume that my axis of rotation is about the center. I'm doing it, like a cheerleader. So in that case, the rotational inertia, which is sometimes given the symbol I, is then just the sum of the individual masses multiplied by the square of the distance from that mass to the axis rotation. So in this case, it would just be m big R squared plus m big R squared. The mass on the left is a distance capital R from the axis of rotation, so it's mr squared. The right ball is a distance capital R from the axis of rotation, so it's also mr squared. So in this case, I would say the rotational inertia is 2 mr squared. As opposed to, what is the rotational inertia if I'm doing it like this? And here's my axis of rotation. In this case, the rotational inertia for the mass on the left is m times the distance it is from the axis of rotation, which is just 0. It's along the axis of rotation. Then the mass on the right is a distance 2r from the axis of rotation. So then this ends up being 4 mr squared. Note, a larger overall rotational inertia, it is harder to get the baton spinning that way compared to if you were spinning it in the center. And just to clarify real quick, because I'm realizing I didn't, let me zoom back up to this definition and augment it a little bit. So when I say distance from the rotation axis, I mean the perpendicular distance. From the rotation axis. To use this baton example, here is my rotation axis, here is my baton with a ball, another ball. And I used this distance here to specify the distance to the rotation axis. It was the line that made a perpendicular, it was 90 degrees from the rotation axis. I would not use this distance or this distance. You might say those are also lines that connect to somewhere along the rotation axis. Those would be incorrect. It is the perpendicular distance. So draw a 90-degree line from the rotation axis to your point, to where the mass is. That's what R represents. All right, so I'll just write down perpendicular distance. What if I do the baton again? But now I'm rotating it along this axis of rotation. So that's this sort of motion. In this case, the inertia, again, add up all the masses times their perpendicular distances. In that case, both of the distances are just 0. The rotational inertia is 0 in this case. If you had a very thin rod with 2 point particles, it essentially would have no rotational inertia. You could rotate it for free. In truth, the masses have some sort of physical shape, so it's not exactly 0. But you can see that this number is much smaller than 2 mr squared or 4 mr squared. What about an extended object? I have a baseball bat. And it's made up of billions and billions of particles. And I want to rotate it about the handle. There's a little bit of mass here, another mass here, another mass here, another mass here. Each of those have some distance from the axis of rotation, R1, R2, R3, R4. And each of those have a little bit of mass, dm, dm. I think you might see where we're going here, dm. And we want to know, what is the overall rotational inertia? It is again defined always as you take all the masses and you multiply by the squares of their perpendicular distances from the axis of rotation. But as you break the object up into smaller and smaller little mass bits, this becomes in general r squared dm. So if you had something with some sort of physical shape, you could evaluate this integral to get the rotational inertia about your given axis of rotation. Remember, this always requires that you specify what the axis of rotation is, because that matters. So for example, let's take the rod, which let's assume it's a very thin rod that has some uniform density. So it could be thin rod with uniform one-dimensional density. And I might use lambda as the quantity there. So it might be, some mass over the length, like what we talked about in the last lecture, if it's one-dimensional. And here's my rotation axis. I'm rotating about the center of the rod. And I'm specifying that the rod itself has some length L. Now what I could do is I could break that rod up into a bunch of tiny, tiny, tiny little pieces of mass, calculate their distance from that rotation axis for each of those tiny little masses, and add them all up. So that would amount to saying that my rotational inertia is going to be an integral from negative L over 2 to L over 2 of r squared dm. The limits in that case is because I'm putting the rotation axis at 0, and I'm going to the left half of the rod and to the right half of the rod. But we saw before of how we can write dm as the uniform density times, d, I guess I could write it as dx, for example. Actually, I realized I skipped a step. These limits don't make sense for this integral. That's ultimately what we're going to do. But those limits were limits on length, not mass. I'm integrating over mass. So I could write this as lambda integral of, I guess I could replace this now with x squared dx, where for x I'm going from negative L over 2 to L over 2. Then in this case, it becomes lambda. I guess the integral becomes x cubed over 3 from L over 2 to minus L over 2, which then evaluates to 2 over 3 lambda times L cubed. No, sorry. I guess it's 1/3, but then this becomes 2 over 2 cubed. So that becomes 2 squared. Yes, there we go. All right, so this is lambda L cubed over 12. But lambda itself, if you look up here, was just m over L. So we could always just write this as mL squared over 12. It could be one example of the rotational inertia of a thin rod about the axis of rotation that is right down the center of the rod. Now these sorts of integrals, right, this was the simplest case of doing one of these integrals. These sorts of integrals can get quite involved. So your book has already computed a bunch of them for you. And for things that we will do, we will just take these as a given. Essentially, if I give you a bunch of point particles, then I assume you're okay evaluating the sum, adding the mass times the radius squared for all the particles. But if it's extended objects, we can use this table of 9 objects. So for example, the hula hoop, the hoop about the central axis, that is saying, you know, this sort of rotation, for example, where the hoop is assumed to be very thin. Versus the second one where it's the same sort of idea, but it assumes that the hoop has some sort of thickness. We can't ignore the thickness of the hoop. Versus a thick rod, you know, that you're rotating like this, as opposed to the thin rod in the center, which is what we just computed, where we assume it's just a very thin wire. And then it gives, you know, here's the same kind of thick rod, but instead of rotating it like this, we're rotating it like this. And you get a different rotational inertia. Then you have a shell, so an empty ball, you have a filled solid ball. You know, again, here's the hoop, but through a different axis of rotation. So the one in the middle bottom is this, which is a different kind of rotation. And then the lower right is a slab. These we can take as a given. So for example, if I said, what is the rotational inertia of the baton? Where the baton has 2 masses m and m. This is some radius r. But the rod itself is also thin and has another mass. Let's say it's also m. You know, it's a nice, it's a balanced rod, where all of these things have the same mass. What then is the rotational, and we are rotating again about the center. The rotational inertia is then the sum of the individual inertias. So that would be mr squared for the ball on the left, mr squared for the ball on the right. And then if we look at our diagram here, it looks like the center one is the one we need. A thin rod that has some mass m, some overall length L. So we have to be careful here. In this case, L corresponds to 2r in our problem. And it's 1/2, or 1/12 rather, that quantity. So 1/12, the mass of the rod, which we also said was m, times the full length of the rod squared. So the full length of the rod squared is then just 2r squared. So then that looks like it's 2mr squared again for the balls, plus 2 squared is 4. 4 divided by 12 is 1/3, so 1/3 mr squared. So then this looks like it is 7/3 mr squared. Would be the rotational inertia for the baton, where we can't ignore the baton's mass. Though notice, if we go back up here, where did we do this? Before, when we could ignore the baton's mass, we got something like 2mr squared, where now we got something that's not quite 2mr squared, but is slightly bigger than 2mr squared. The baton itself didn't contribute that much to the rotational inertia because most of its mass is very close to the rotational axis. It's the farther away you get from the rotational axis that starts to make things have more rotational inertia, harder to get things to rotate if they are far away from the rotation axis. All right, I think that's a good place to stop. There's also the parallel axis theorem, which we will need for this, but I can do that at the beginning of the next lecture. The parallel axis theorem is, what if I want to take one of these and I want to shift the rotational axis a little bit? Do I have to redo the entire integral? And it turns out as long as the axis is parallel to one of the axes that are drawn in this diagram, you don't. There's a nice little convention you can use. All right.